So I hope you remember this. Test 2 is on Thursday, 12:30. Sign into Zoom. You'll take the test on Canvas like you took test 1 on Canvas. I've now posted it on Sunday, a practice test 2. It has different point assignments for the different types of questions, multiple choice, numerical answer, and the fully worked out problem. There are a little different numbers of the numerical answer problems, but it's basically the same style, the same sort of format as test 1. Just a reminder that the content is the material that we cover since test 1. So it's the material on chapter 5, which was work and energy. It's the material on chapter 6, which was impulse and momentum. And it's the material we're covering now on circular motion and universal gravity. I've posted on this slide the chapter and section numbers that are relevant to the test. There was originally a mistake here. It said 7.1 to 7.4. That was from an old textbook. It's now 7.1 to 7.5 in the new version of the textbook. Okay, let me switch on the chat and then I'll get started with today's lecture material. So today's class actually contains a couple of enormous scientific breakthroughs. One of them, perhaps the biggest of the two breakthroughs, one of them was the discovery by Isaac Newton of what we call nowadays universal gravity. And it was an explanation of both the sort of astronomical scale celestial motion of planets, moons, etc., and simultaneously the everyday scale terrestrial motion of falling bodies, falling objects, etc. And it was really, in physics, it was a huge event. It was a landmark event. It's hard to overemphasize the importance of this event. So that's one breakthrough today. The other breakthrough today is that out of universal gravity, we'll discover a way of measuring the mass of something that's important to us, measuring the mass of the Earth. So out of this theory of universal gravity came sufficient understanding to actually determine the mass of the Earth on which we stand or sit in our everyday lives. Okay, so as I say, Isaac Newton's law of universal gravity is well known in physics, is renowned in physics for its what we call unification, joining together of the celestial planetary motion and the terrestrial falling body motion in one theory of gravity. It's actually built on the shoulders of lots of other scientists. And for example, it's built on Copernicus's shoulders and his understanding that the Earth revolves around the sun. It's built on Galileo's shoulders and his understanding of falling bodies, falling with an acceleration 9.8 meters per second squared, and other scientists too. And so it's Newton's law of universal gravity. It's his unification of celestial terrestrial motion, but it's built on the work of others, like science is always built on the work of others. Okay, so I want to begin today's class with just exploring, comparing celestial and terrestrial motion. And then we'll work our way to the discovery, to the uncovering of universal law of gravity. And then we'll look at some applications, some examples of law of gravity. For an example of celestial motion, I picked the motion of the moon around the Earth. And for an example of terrestrial motion, I picked an apple falling towards the ground. So those are just going to be our two examples, celestial, terrestrial motion. And on this slide, I want you to note how different those two types of motions are. Firstly, they're different in the scale, the size scale of these motions. You know, the apple falls a meter to ground. The moon travels millions of meters around in its orbit. So the motion of the apple to the ground and the moon around the Earth are completely different size scales. Some other things that are different. So the moon is actually traveling at constant speed as it circles around the Earth in its orbit. The apple, on the other hand, is getting faster and faster and faster as it falls towards the Earth along its path. So the motion of the moon, motion of the apple are very different. In one's uniform speed, circular motion, and the other one is changing speed, straight line motion. In some sense, they couldn't be more different. Straight line versus a circle. Speeding up versus constant speed. What could be more different than that? So our starting point here is that the celestial motion of the moon, terrestrial motion of the apple, they're very different types of motion. What could be common about these different types of motion? Well, what Newton realized was that there is common things about the motion of the moon in its orbit around the Earth and the motion of the apple as it falls towards the Earth. And what he first realized was what's common is the acceleration of the moon and the apple. And specifically, that the moon and the apple are accelerating, they're both accelerating towards the center of the Earth. And we have all the physics we need for us now to understand that, right? If you think about, let's look over here on the right-hand side, where we got the apple and it's falling towards the Earth. And here's its straight line path towards the Earth. And we understand now from the first few lectures of this class that this apple is accelerating downwards towards the very center of the Earth. And from the past few lectures, this is now I'm going over here on the left, I've got the moon upstairs here and the Earth downstairs. Whilst the moon is circling around the Earth, its acceleration, its centripetal acceleration, which is this little red arrow here, that's also towards the center of the Earth, towards the center of the circular motion. And so whilst the last slide kind of illustrated the difference between the circular and straight line motion of the moon and the apple, this slide reminds us, based on our kinematics of circular motion, kinematics of linear motion, that their accelerations are actually in exactly the same direction. Both the moon, the apple, accelerating towards the center of the Earth. And so that was a huge realization. I'm going to get my pen working. We've got all about that. And let's go on to the next slide. On this slide, after Newton realized that both moon and apple are accelerating towards the Earth's center, which seems to be a common feature about their motion, that they're both accelerating towards the Earth's center, he wanted to compare the magnitude sizes of the acceleration in the moon and the acceleration in the Earth. And we can do that too. So over on the right here, we have to thank Galileo for this. This is partly why we stand on Galileo's shoulders, or Newton standard on Galileo's shoulders. Galileo told us that the acceleration of the apple, or any dropped object, falling body, has an acceleration of 9.8 meters per second squared towards the ground, towards the Earth's center. So we know that. We also have learned that whenever you've got circular motion, you've got centripetal acceleration, and the size of that acceleration depends on how fast you're going around the orbit, and it depends on the radius of the orbit. And we know the moon's orbital period. We know the moon's orbital radius. Actually, Newton knew the moon's orbital period and the moon's orbital radius. And so you can calculate the acceleration by taking the square of the speed that it travels around the circumference of its orbit, divided by the radius of its orbit, and you get 0.0027 meters per second squared. And we actually calculated that in an earlier class last week. And so those are the two accelerations of these two objects, moon, apple, that are accelerating towards the center of the Earth. Now you might say, oh, well, that's disappointing. It's disappointing because it looked like there was something common about their accelerations. Their accelerations were both towards the Earth's center, but now it looks like, well, one's a big, relatively big acceleration, the apples, one's a relatively small acceleration, the moon's. What Newton realized is that, yeah, they're very different values of accelerations. 9.8 meters per second squared and 0.0027 meters per second squared. But they are related, they are connected. He spotted that relation, that connection. And here it is. This is like from his notebook. At the time, Newton knew the radius of the Earth. Here's the radius of the Earth. I called it RE. And he knew the radius of the moon's orbit. Here it is. I've called it RM. And comparing them, he saw that the radius of the moon's orbit is about 60 times the radius of the Earth. What he realized was when he looked at the acceleration of the apple falling towards the Earth and the moon accelerating towards the Earth, that the accelerations were in a ratio of 1/60 squared. So the acceleration of the moon is 1/60 squared of the acceleration of the apple. So they were two very different numbers, the acceleration of the moon, acceleration of the apple. But they're related to the very different distances between the moon and the center of the Earth and the apple and the center of the Earth. The moon is 60 times further away from the center of the Earth. The moon's acceleration is 60 squared times smaller compared to the apple's acceleration. And that was a huge, important realization that secured this understanding that there was something common to the motion of the apple and the moon. And what's common to the motion of the apple and the moon, the apple falling straight towards the Earth's surface, the moon circling around the Earth, is that there's a common force, a universal gravitational force that is responsible for those two different types of motion. So let's take a look at that. So at this point, after thinking about acceleration, the directions of the accelerations of moon and apple, thinking about the sizes of acceleration of moon and apple, Isaac Newton hypothesized that there was a uniform influence, uniform force responsible for both these motions. He proposed that the terrestrial motion of the falling apple, the celestial motion of the orbiting moon are due to a common force, due to a single force. And that's gravity, universal gravity. And he was able to figure out the properties characteristics of universal gravity. So here's one key property. I do this every time. Here's one key property of gravity. If gravity is going to cause the acceleration, gravity of a small apple, a large apple, a mouse, an elephant, all these things with different masses, then the gravitational force that's causing that common gravitational acceleration, 9.8 meters per second squared, that gravitational force must be in proportion to the masses of the mouse, the elephant, the small apple, the large apple. So you feel the gravitational force in proportion to your mass. And he reasoned you also exert a gravitational force in proportion to your mass. He reasoned that mass itself is the origin, the source of gravity, of universal gravity. And specifically, he said that the force of gravity between two objects, any two objects, is going to be in proportion to the product of the two masses of those objects. The one that's exerting the force, the one that's feeling the force. And that's all I've written down here. This is simply a statement, his idea that to explain the facts, then the gravitational force must be due to mass. And the force between two bodies must be proportional to the product of the two masses of those two bodies. So here I imagine body number one and body number two. And so the force is proportional to m1 times m2. For the case of the apple falling towards the earth, m1 and m2 are the mass of the earth and the mass of the apple. In the case of the moon circling around the earth, the m1 and the m2 would be the mass of the earth and the mass of the moon. So that's one ingredient in universal gravity. It's obviously a key ingredient. It's saying where the force comes from. It comes from the fact that objects have mass, and it comes in proportion to that mass. Second key ingredient is here. To account for the fact that the moon's acceleration was 60 squared times smaller than the apple's acceleration, where the moon is 60 times further away from the center of the earth and the apple is from the center of the earth. Newton secondly reasoned that the force must fall off with distance between the masses, and it must fall off in a very special way. It must fall off as the square of the distance. So if you double the distance, it will get 4 times smaller. If you multiply by 3 the distance between two masses, it will get 9 times smaller, and so on and so forth. So if we made the distance 60 times larger, then the force would fall off by 60 squared times the amount. And so that's the characteristic dependence of the force between masses on the separation of the masses. And we call that, we give it a name, we call it an inverse square law, and it's characteristic of gravity. So that's the second ingredient in Newton's law of gravity. Okay, so on this slide, I put all those things together, which is obviously what Newton did. He put all these things together, all these ideas about universal gravity together, that mass is the origins of the force, that the force gets weaker with the square of the distance between the masses, and also that the force is always an attractive force. Masses are always pulled together by the force of gravity. They're never pushed apart by the force of gravity. It's always an attractive force. And so that whole idea, concept, is summarized on this slide. So summarized in this equation, this is Newton's law of universal gravity as an equation, is summarized sort of in this picture. In this picture, we're thinking of two masses, this ivory one downstairs over here on the left, this blue one upstairs here on the right. And they've got masses m1 on the left, m2 on the right. And so they're going to interact gravitationally. They're going to attract one another gravitationally. And that gravitational attraction, well, it depends on the two masses and it depends on their separations. That's called R12 here, the distance from mass number 1 to mass number 2. And that interaction creates an attraction on the left-hand mass. It's attracted to the right-hand mass. It creates an attraction on the right-hand mass. It's attracted to the left-hand mass. And those attractions are those forces here. F12 is the force experienced by 2 due to object number 1. F21 is the force experienced by object number 1 due to object number 2. And here is, upstairs here, here is the equation for that force. To say it depends on the product of the masses of the things exerting and experiencing the force, the inverse square of the separation between those masses, and also a constant, a number that sets the scale for gravitational forces. It would determine, depending on whether it's big or small, how big a force gravity is. And that number is kind of interesting. It's called Newton's gravitational constant. Here it is. It's actually, in SI units, it's actually very small. It's just about 7 times 10 to the minus 11. So it's a tiny, tiny number. And that's really a reflection that, you know, we think of gravity as a big force. It's a big force in our everyday lives. If we jump off a tall building, it would be a big force pulling us down and we'll get hurt. But really, gravity is actually a very feeble force, a very weak force. It's the most feeble, most weak force we know in nature. All the other forces that we know in nature are stronger, larger than gravity, would have larger associated constants than the gravitational constant. So actually, in our everyday lives, we think of gravity as a really big force, but in physics world, gravity is the smallest, weakest force of nature. Now, in our everyday lives, gravity is a big force because the Earth is so massive that that huge mass of the Earth creates significant gravitational forces on us. But the gravitational force between everyday objects, that would be really, really feeble. That would be really, really small. Anyway, this is Newton's famous law of universal gravity. And as I say, it is a unified explanation. This is an amazing thing about it. I think it's brilliant. It's a unified explanation of both celestial motion like the moons and terrestrial motion like the apples. Okay. Oh, we're at the physics department, complaints department. What are we doing here? Well, there's some explaining I better do. Explaining I better do is that we previously met a formula for the gravitational force. It was mg. And we've now met a new formula for the gravitational force. It's gravitational constant times m1 times m2 divided by r squared. So, I mean, how can I've got two equations for gravitational forces. How can I reconcile these? So that's why you've come to the complaints department. Well, here's the reconciling of these two equations. Let me just say a few words about the original, the original equation that we met, which is this one over here on the left. And then I'll go on and talk about the new equation, universal gravity equation we've met. So the first one The first one was really simply based on the observation by Galileo that all objects fall with the same constant acceleration of gravity, 9.8 meters per second squared. If that's the case, then the gravitational force that's causing that gravitational acceleration must be the mass of the object times the acceleration of gravity. That's where mg comes from. Now, mg is a very useful equation, but in the equation mg, there's no explanation whatsoever. There's no explanation whatsoever of why g is 9.8 meters per second squared, for example. It's just an observation. It's just an experimental fact that the acceleration of gravity is 9.8 meters per second squared, and hence the forces must be m times that acceleration of gravity. And that F equals mg actually just applies to near in the neighborhood of the surface of the Earth. So it's limited scope. The second equation, the one over here on, now gone from the, I was over here on the left and now going over here on the right. This goes far beyond F equals mg. This describes the gravitational force between any pairs of masses, not just between you and the Earth, or a mouse and the Earth, or an elephant and Earth, or apple and Earth, between any pairs of masses, at any separations between those masses. And so this equation, for example, explained, universal gravity explained both the moon's motion and the apple's motion. The other equation, F equals mg, only explains the apple's motion and doesn't explain the moon's motion. So this is a much larger, much larger reach in terms of what it can explain than this equation here had in terms of its reach. The mg equation is just an equation that's very, very handy, very, very useful, but just near the surface of the Earth. The G little m big M over R squared equation, that applies between any masses anywhere, any pairs of masses anywhere. And so that's how we kind of reconcile those two equations. There was a question in chat. I just saw it. Let me just go back to the previous slide if I can. Normally I can only do that accidentally rather than deliberately. So the question was, are F12 on the sketch and F21 on the sketch going to be the same? They're the same size. They're oppositely directed. They have the same size. So they are an action and reaction pair. That's a really good question. They are action and reaction. Mass 1 creates a force on mass 2. Mass 2 creates a force on mass 1. Those forces are equal size. They're opposite directions. That's what's shown in the picture by the directions of the forces. And the equation would get the same sizes if you just reorder the masses and reorder the 1s and 2s. Okay, I want to show you now how incredibly powerful this universal law of gravity is. And I want to show you how with this universal law of gravity, now there's, instead of just observing, measuring the acceleration of falling bodies, 9.8 meters per second squared, you can actually, with this theory, with this universal gravity theory, you can calculate the acceleration of gravity near the surface of the Earth. So let's do that. The way I'm going to do it is equate two equations, the two equations we just met. So here's sort of Galileo's version of gravity, that all objects fall with the same acceleration of gravity. That's on the left-hand side here. And here's kind of Newton's universal gravity. that mass is responsible for gravity. And the gravitational force between two masses is in inverse proportion to the square of the distance between the centers of the two masses. So I'm just equating those two equations that would both apply to an apple near the surface of the Earth. Now, if you equate those equations, the mass of the apple, that's the little m here, cancels out. And what you get, this is fantastic, I love it, is an equation for the acceleration of gravity, which of course we know the acceleration of gravity from Galileo is 9.8 meters per second squared, but here we got a prediction for the acceleration of gravity. Acceleration of gravity is the gravitational constant times the mass of the Earth divided by the square of the radius of the Earth. That's the distance of the apple from the center of the Earth. And all those numbers you know, right? I've written them out here. Here's the gravitational constant. Here's the mass of the Earth. I looked it up with Google. Here's the radius of the Earth. I looked it up with Google. And I could plug them all in. And I did plug them all in. If you plug them all in, you get 9.8 meters per second squared. It's now a prediction. And we're testing the theory of universal gravity. It's no longer just an experimental fact, an experimental observation. So it's really a fantastic thing. Now, there's a little sad note to this, I think. I don't want to make you upset, but there is a sad note to this, that Newton knew a lot of numbers, like the radius of the Earth, like the radius of the moon's orbit. But he didn't know the mass of the Earth, and he didn't know, ironically, he didn't know the value of his gravitational constant. And so Newton himself, although he discovered the universal law of gravity, he couldn't check its most famous prediction by calculating the acceleration of the apple near the surface of the Earth. He couldn't do that because he couldn't do what we just did. He didn't know the mass of the Earth, and he didn't know the gravitational constant. Okay, there's a couple more. Lillian and Tyler asking me a little bit more about that. Those two apples, those two objects attracting one another. If one is opposite, does that mean one will be negative? The vectors are opposite. So, you know, if you had the vectors along the x-axis, you know, one of the force vectors you could represent by a positive value, and one of them you could represent by a negative value. Tyler says, if two objects are on a table, is there a force attracting them together? Yeah, there actually is a gravitational force attracting those two objects on a table. And actually they're each attracting the table, and the table is attracting them also. And we're going to talk about that. Because that's exactly this slide here. So one of the amazing predictions, and Tyler must be some sort of genius as well, is that universal gravity predicts that we're not just attracted to the Earth, but we're attracted towards each other. We're attracted to all objects around us, and all objects around us are attracted to us. And that includes if you have two apples, right? Those two apples are attracted to one another by the universal gravitational force. And here's the interesting thing. And one thing that's interesting about this is it wasn't done until nearly 200 years after Isaac Newton had died. But if you could measure the force between two objects whose masses you know and whose separations you know, then you could, if you could measure that force of attraction, you can determine the gravitational constant. So if you know mass m1, you know mass m2, you know the separation r between them, and you measure their force, the only unknown quantity that's inside the universal law of gravity is the gravitational constant. You can find the gravitational constant. That's how the gravitational constant was found. It wasn't found by analyzing the moon going around the Earth or the Earth going around the sun, it was found by measuring the gravitational attraction between two everyday objects, two known masses. Once you know the gravitational constant, you could then determine, or we determine the acceleration of gravity, but actually acceleration of gravity is known. Once you know the gravitational constant, you can actually figure out the mass of the Earth. And it's how we measure the mass of the Earth. Measure the mass of the Earth by knowing universal gravity and the value of the gravitational constant. You can then measure the gravitational attraction between the apple and the Earth, or you and the Earth, and figure out what the mass of the Earth must be to create that gravitational attraction between the apple and the Earth, or you and the Earth. So those are amazing things you can do with universal gravity. So this is actually this famous experiment. Maybe this is like 150 years ago now, something like that. And it was by this famous sort of scientist, kind of nobleman, whatever, owned a castle, built his own lab, Henry Cavendish. And it was really a rather clever experiment, because to measure the force between two apples or to two everyday objects, the challenge is that that force is really, really tiny. Like, you know, I said we're all attracted to each other by gravitational force, and every object around us by gravitational force. We don't all clump together. We don't all clump together because that force is so weak, so feeble. And so this is the experiment that Henry Cavendish developed to measure the gravitational force between known masses. Actually, what he did, let me get the pen working. So here's blue mass, uppercase M, and ivory mass, lowercase m. They're going to attract. And actually, in this experiment, it's quite clever. He had a copy of these masses. So uppercase M, lowercase m over here on the right-hand side, and they're also going to attract one another. And he had the two copies just to keep his arrangement in balance. You see, the ivory masses are hanging from a thin wire. When the ivory mass on the left is attracted to the blue mass on the left, and when the ivory mass on the right is attracted to the blue mass on the right, that turns this horizontal bar that's connected them, that's supporting them, and it rotates this thin wire. And when that wire rotates, it rotates this mirror. It's all brilliant. That's attached to the wire. And he shone a light on the wire, and he looked at the image of the light on the wall. And the gravitational attraction between the pairs of masses here causes the light to swing on the wall. And he was able to measure the force in that way. It was really a brilliant, it's called a torsion balance. It's been used in lots of different experiments in physics, science. But here's I think the greatest ever, most brilliant use of torsion balance. These forces between these masses, they're nanonewton forces, piconewton forces. They're immensely small. And so they're very, very hard to measure. And so you need a very, very careful setup. You need very, very careful measurements. And this is how we did it. But anyway, he knew the separations are between the masses. He knew the values of the masses. And therefore, through the universal law of gravity, if you know the masses over here on the right and the separation over here on the right, and you know the force over here on the left with his torsion balance, then you can solve for the gravitational constant. And that's what he did. And it took 200 years after Isaac Newton's universal law of gravity. Okay, let's look at an example now. let's do a little calculation. And I'm going to calculate the gravitational forces on the moon. And specifically, if you think about moon, moon is in orbit around the Earth, and the Earth's in orbit around the sun. There's actually gravitational forces on the moon and due to both the sun and the Earth. And we're going to compare the force of the gravitational force of the sun on the moon with the gravitational force of the Earth on the moon. And so we're actually going to calculate in this problem, we're going to calculate this ratio here. Fe is the Earth's force on the moon. Fs is the sun's force on the moon. And we're going to see, it's an interesting question. Well, now we know from universal gravity that both the sun and the Earth are exerting forces on the moon. Does sun or Earth create a bigger force? Let's compare them. And that's what I've done on this slide. So on this slide, all I really did was, here's the force, Fe is the force of the Earth on the moon. And Fs is the force of the sun on the moon. And I'm just going to, in both cases, substitute in the universal law of gravity in the numerator and the denominator for these two forces. Now, here's the arrangement that I'm thinking about over here. Here's the sun. Here's the Earth going around the sun. And here's the moon. So I got the sun in orange, obviously. I got the Earth in blue, obviously. I got the, maybe I should have, the moon we know is made of cheese, so maybe I should have made it yellow, but I made it gray. And I want to compare the attractive force of the Earth on the moon. So that's this little blue arrow here, and the attractive force of the sun on the moon. This should be F subscript, F subscript sun is correct. Okay, so I'm going to compare those two forces using the universal law of gravity. So here's the universal law of gravity for the Earth's interaction with the moon. Here's the universal law of gravity for the sun's interaction with the moon. So in each universal law of gravity, there's the gravitational constant, then there's the product of the masses, mass of the Earth times mass of moon, mass of sun times mass of moon, and then divided by the square of the distance between either the Earth and the moon or the sun and the moon. Now, when you write it out like that in that ratio, a number of things cancel each other out. And we don't need to know them, or we don't need to substitute them because they're the same in the numerator and denominator. So the gravitational constants cancel out, and the mass of the moon, which is common to both force evaluations, that cancels out. And we find that the ratio of the two forces is given by this ratio involving the masses and the radii of the orbits. Mass of the Earth, mass of the sun, radius of the moon's orbit around the sun, and radius of the moon's orbit around the Earth. And we can plug all those things in. And so that's what I did downstairs here. The smaller mass upstairs here, that's the mass of the Earth. Larger mass downstairs here, that's the mass of the sun. They're, about 1 million times different. So the sun is pretty heavy compared to the Earth, mildly. And then there's the radius of the orbits, the moon around the sun and the moon around the Earth. So the larger number here is this larger distance. And then the smaller number here is this smaller orbit's radius. And they're different by a lot too. You know, the size of the Earth or the moon's orbit around the sun is about 500 times the size of the moon's orbit around the Earth. So they're very different also. But what's interesting, right, is if you plug in all the numbers, you get a ratio that's about a half. So these are very different scales, astronomical scales, between the radius of the Earth's orbit, the moon's orbit around the sun, and the radius of the moon's orbit around the Earth. They're very different scales, different by a factor of 500. They're very different masses creating these forces. The sun is the scale of 1,000 times heavier than the Earth. But in the calculation of the forces, because the lighter object, the Earth, is close to the moon, the heavier object, sun, is far from the moon. The forces are similar size. Okay, there's a couple of questions. Okay, so there's one question, why am I multiplying by r? So this is RE squared in the numerator when I plugged in the universal law of gravity. I'm dividing by RE in the numerator. And that is equivalent to multiplying the denominator by RE. So I just moved this RE from upstairs downstairs. And likewise for the sun's radius, it was dividing in the universal law of gravity for the sun, dividing in the denominator, and so I moved it up and multiplied by it in the numerator. So that was just the algebra, rearranging the equations to make them look a bit simpler. Okay, there's a second question there. Wouldn't the radius of the moon to the sun orbit change as the moon rotates about the Earth? That's a good question. I've got a quiz question. It's sort of a bit related to that. The point is that my picture of the sun, moon, and Earth wasn't really drawn to scale. So the Earth's orbit radius is the scale, let's call it 1,000 times, it's 500 times that of the moon's orbit radius. So in reality, if this is the radius of the Earth's orbit, the radius of the moon's orbit would be in some tiny, tiny dot here. So on that scale, the moon is always about the same distance from the sun. Okay, let me press on. And I got a quiz, so I'm going to post this quiz for you. In A, because the moon and because the Earth and the sun are on the same side, they're both over here, then they're both attracting the moon towards the bottom left. In B, the sun and the Earth are on opposite sides of the moon. And so they're attracting the Earth in the opposite directions. The sun is attracting the moon down to the bottom left, and the Earth is attracting the moon up to the top right. So in A, the forces are in the same direction. The sun and the Earth pull in the same direction. In B, the forces are in opposite direction. The sun and the Earth pull in opposite directions. And so in A, the forces pulling in the same directions work together and add together to make a larger total force. In B, the forces are in opposite directions. They work against one another. They partially cancel one another out. And the force is a lot smaller in the configuration in B. And so the correct answer is that A has the larger force. Configuration A has the larger force. Configuration B has the smaller force. This force on the moon is bigger in A and smaller in B. That is for some reason I thought I got it the wrong way around in the lecture quiz, but it's the right way around in the lecture quiz. There's a question that says the question was asking total force, though not net force. Total force and net force have exactly the same meaning. Let me just make that clear. There's no different. Net force means the total force. Total force means you've added up the force vectors, and net force means you've added up the force vectors. So whether I say total force of gravity or whether I say net force of gravity, that's the same question. Total and net mean the same. And they both mean adding up the force vectors. Okay.
Excuse me, sir. Could you repeat what the answer was for that? Sorry.
Oh, yeah. The answer is that the configuration A has the larger force. The configuration B has the smaller total force.
Okay, thank you.
Sure. Okay. Well, last topic I want to discuss today is in relation to gravity, universal gravity, is we talked about the universal gravitational force between two masses. I want to move on from this sort of force perspective to an energy perspective for universal gravity. And we did this earlier on in the semester, right? We talked about, firstly talked about forces, and then we talked about energy. And we said that they're just different ways of thinking about the interactions between objects. They're different ways of solving problems. They're different ways of understanding problems. And so we're now going to not just look at the universal force of gravity, but we're going to look at the corresponding gravitational potential energy. So we're going to move from the force perspective to the energy perspective. Now that means I've got to reconcile a second set of equations. And so I've written those upstairs here in this slide. We talked about gravitational potential energy earlier. We said it depended on the elevation of an object above the surface of the Earth, and we had this equation for it. This was gravitational potential energy earlier. And this equation we got from the gravitational force, mg. Now I'm going to show you a new equation for the gravitational potential energy. It's this one here. And this one comes from the universal law of gravity. This equation here. And so just like we had to reconcile an old version of the gravitational force with a new version for the gravitational force, we got to reconcile an old equation for gravitational potential energy with a new equation for gravitational potential energy. But really the reconciliation that we have to do for the energies equations is the same reconciliation that we had to do for the force equations. So mg, this equation for the force, was simply based on Galileo's observation of constant acceleration for falling bodies. And that meant that there was a force, mg, that must be responsible for that constant acceleration. But there was no explanation in Galileo's understanding of how that force worked or how that acceleration worked. When we met universal gravity, well, that's a much broader, bigger theory that all objects experience gravitational attractions. And it also explained the acceleration of gravity on Earth. And so it was a deeper, more fuller understanding of how gravity worked. And so that was the reconciliation between the force laws. And it's really the same reconciliation between the two equations for gravitational potential energy. The first one, mgh, well, that just applies for objects near the surface of the Earth. If you lift them up or pull them down near the surface of the Earth, that's how gravitational potential energy of the object in the Earth changes. The second equation, G equals m1, m2 over r, not r squared, that's the gravitational potential energy between any pairs of masses. It might be the apple and the Earth, with the apple near the surface of the Earth. It might also, though, be the moon and the Earth. The first equation didn't apply to that. It might be the gravitational potential energy associated with the interaction between two apples themselves. MGH doesn't apply to that either. So again, the gravitational potential equation on the left, that applies to a very specific situation. Objects near the surface of the Earth and their gravitational potential energy. And it doesn't explain why the acceleration of gravity is 9.8 meters per second squared. The second equation on the right, that has much broader applications. The gravitational potential of energy between two apples, between an apple and a mouse, between a mouse and an apple, a mouse and an elephant, and between the moon and the Earth. So it applies to all those situations. And it has an explanation, a deeper understanding of where that potential energy comes from. It's a consequence of the interaction between the masses. And so that's how we reconcile those equations. Okay. That energy perspective allows you to solve some problems that are difficult with the force perspective. Some problems involving universal gravity can be explained from the energy perspective with that equation for gravitational potential energy that are much more difficult to solve from the force perspective with the gravitational force law. And so I wanted to show you an example of that. Now, I want to mention the fact that sooner or later, we have to find a way to escape from the Earth. And sooner or later, we have to find a way to escape from the Earth because the sun, which keeps us alive on the Earth, that's going to run out of fuel. And when the sun runs out of fuel, the sun's going to go dark and nothing can survive on Earth. And so ultimately, for civilization, we have to get away from the Earth. Now, to be fair, the sun's not running out of fuel. You don't need to leave class now, right? It's not running out for 5 billion years. So personally, at least I don't have to worry. But ultimately, civilization has to worry about this. And so a famous physics question is how fast, what velocity do you need? What speed do you need to blast off from the surface of the Earth? Fire a rocket and fly off from the surface of the Earth and get away from the Earth's gravitational pull, to escape the Earth's gravitational pull. Now, this is a problem that is difficult to solve from a force perspective, but is much easier to solve from the energy perspective. So that's why I'm going to solve this one. We'll solve it from the energy perspective. And we're going to figure out this important speed that a rocket needs, or that you would need, to blast off from the surface of the Earth and actually to completely escape from the Earth's gravitational pull. Okay. So here's my solution of this. And basically, I'm going to find this escape velocity, we call it, how we escape from Earth, by energy concepts and energy conservation. And I started with a sketch. The sketch is here. And sketch is important for this picture. So over here on the left, this is Earth, and this was where I'm starting. And then over here on the right, this is meant to be deep space, far away from the Earth. And this is where I'm ending up. And here's my spaceship. And here's the little dog in the spaceship. And we're traveling away from the Earth to deep space. And we're going to apply energy conservation, kind of like we applied on a roller coaster, for example, where we started at the top of the roller coaster and we rode down to the bottom of the roller coaster and we were able to figure out our final speed in terms of our initial height. We're going to do the same sort of calculation here. So we start off on the left, and there's two forms of energy that I'm going to worry about: kinetic energy and gravitational potential energy. And then we're going to end up over here on the right, and there's two forms of energy that I'm going to worry about: gravitational potential energy and kinetic energy. So the space rocket blasts off, and so it has some initial kinetic energy by virtue of its motion, and that's given by this equation here, 1/2 mv squared. And that v is the velocity or the speed of the spacecraft. So the spacecraft has some initial kinetic energy determined by speed, and the spacecraft here also has some gravitational, the spacecraft and Earth together have some gravitational potential energy. And it's this little equation here, minus g. I got a feeling I missed the minus sign on the last slide. Did I do that? Let me just head back, because that would be a mistake that I got to correct. Yeah, so this is naughty. There should be a minus sign in here. And I will correct that. There's a little minus sign here. And so this is that equation for the initial gravitational potential energy. And it's the gravitational potential energy of the rocket and the Earth system. Big M is the mass of the Earth, little m is the mass of the rocket, and RE, that's the separation between them, which is the radius of the Earth to begin with. Then so I blast off, and like 1,000 years later or whatever, I'm in deep space, and I just make it to deep space. So when I just make it to deep space, my velocity, if I'm just going to make it there, I just escape the Earth, is going to be 0. I've just come to a rest as I escape the pull of the Earth's gravitational force. And my gravitational potential energy, what will that be? Well, essentially that will also be 0. The gravitational potential energy of me and the Earth, that system, will also be 0, because now I'm really far from the Earth. And if I'm really far from the Earth, right, r is this distance that I am from the center of the Earth, that's got really, really large, then the gravitational potential energy has got really, really small. And so this is what I really mean by being in deep space versus being at the surface of the Earth. In deep space, if I just get there, I've no longer got any kinetic energy. And my gravitational potential energy associated with my interaction with the Earth has shrunk to nothing. But when I was blasting off, I had lots of positive kinetic energy because I was going fast in my space rocket. And I had lots of negative gravitational potential energy because I was relatively close to the center of the Earth. But the point is that that total energy that I started with, gravitational and kinetic, must be equal to that final total energy that I end up with, gravitational kinetic, because energy is conserved. And so this initial energy and this final energy in red and green here, they must be the same. Well, that gives us a route to solving the escape velocity, the V. If I substitute in the expression for the initial gravitational potential energy, that's here. Substitute in the expression for the initial velocity, initial kinetic energy, that's here. Substitute in the expressions for the final gravitational potential energy and the final kinetic energy, that's these guys here. Then I build this equation in this equation, the m's, the mass of the space rocket, or maybe that's the mass of me or the dog if we were just trying to fly away from the Earth, those cancel out because they're common factors. And I can rearrange this equation for the escape velocity. I just have to take the term involving the gravitational constant over to the other side of the equation, multiply by 2, that's where this 2 comes from. Take the square root, that's where this square root comes from. And you get an equation for the escape velocity in terms of the mass of the Earth, the radius of the Earth, and the gravitational constant. And I just substituted in the gravitational constant, the mass of the Earth, and the radius of the Earth. And I did this little calculation here, and here's the result. So this is the sort of famous escape velocity from Earth. If you could fire a bullet straight into the air, fire a cannon straight into the air, or fire yourself from a cannon straight into the air with 11,200 meters per second speed, you would have sufficient speed to break free of the gravitational pull of the Earth and to ultimately escape from the gravitational interaction with the Earth. That equation that we just solved, so this little one over here, that's a general, actually, it's more general than just how much speed you need to escape from the Earth. It's how much speed you need to escape from any object. So you could apply this to escaping from the moon or escaping from Mars. What escape speed there is for the moon, what escape speed there is from Mars. You could apply it to your escape speed from the surface of an apple. You could use the equation for any of those. So if you do it for the moon, it's quite a bit smaller. It's 2,000, more than 2,000 meters per second. This is what, the Apollo astronauts had to overcome to get back to Earth. On Mars, it's quite a bit bigger, nearly 2.5 times bigger. And that's the problem, probably the biggest problem with going to Mars. It takes a long time. The biggest problem is actually when you get there, somehow you've got to get back off to come back home. And the escape velocity is a big problem to get home from Mars. And if I didn't put apple, what's the escape velocity for an apple? Well, if you did the same calculation for an apple, the mass of the apple is tiny. The radius of the apple is tiny too. But the mass of the apple being tiny wins out of the radius of the apple being tiny. The escape velocity would be absolutely minuscule. Absolutely tiny to escape the gravitational pull of an apple. It's easy to get away from the gravitational pull of the apple. Okay, anyway, that's an example of the energy perspective and the universal law of gravity. There's a couple of questions on this one in the chat. Why is the final kinetic energy 0? I put the final, so that's a good question. I'm calculating the escape velocity to just manage to escape the pull of the Earth, the gravitational attraction of the Earth. And just escaping the gravitational attraction of the Earth is when you get far away from the Earth into deep outer space, but you've got no more kinetic energy left. If you have more kinetic energy than that to start with, well, you're escaped and you'll still have some remaining. So you've kind of more than escaped. If you had less than that escape velocity, well, you try and escape and you can't make it, you're going to get pulled back in. So the escape velocity is a single number that if you exceed, you break free. And if you don't exceed, you get trapped. What is RE? 6,390 kilometers. That is the distance between where the rocket blasted off at the surface of the Earth and the center of the Earth. So that's the distance that's in the universal law of gravity. It's the radius. If you blast off from the surface of the Earth, it's the radius of the Earth. Just like the apple is at the radius of the Earth. If you apply Newton's Newton's law of gravity, universal law of gravity to it. Okay. Well, let me end there. Good luck with test 2.